Okay, welcome to our presentation on cylinders, and we're going to talk about difference of area of cylinders specifically. So a cylinder, a lot of times it's called an actuator. Can be several different types of cylinders. The one that we talk about most often is a double-acting single rod cylinder. Double-acting meaning that it can both extend and it can retract. Okay? So for it to extend, we need to introduce flow into what we call the cap end. So when we have fluid flowing into the cap end, then we're going to have our volume in our cap end is going to be expanding, okay, and then that causes the cylinder to extend, and then of course the volume in the rod end is going to be reduced and causing flow to come out of the rod end port. Of course, for it to retract, we have the opposite happen. So we have flow introduced to the rod end port. That causes the rod end volume to expand, causing the cylinder to retract. And then, of course, we have fluid coming out of the cap end port. I've been asked why the cap end is called the cap end. Typically because of how cylinders are made. There's usually what we call the cylinder itself, the cylinder body, okay, which is just basically a tube of some sort. On one side we have a cap, which basically would be like a cap on a bottle or something. It is screwed on or welded on. On the other end we have a rod, and that rod is connected to what we call the piston. So right here is the piston. That piston is what actually moves back and forth, and then we have a rod that's connected to the piston. Sometimes we have what's called a double rod, where we have rods coming out both sides. So there is no cap end because they're both rod ends, right? In that case, we just define whether an A or a B side, or just depending on the application, we say whether it's extending or retracting. Sometimes cylinders are single acting. So for example, if we look at a cylinder, we can have a cylinder that has only one port. So when flow is introduced to the port, the cylinder of course extends, just like on a double acting cylinder. But to retract, you simply allow there to be a path to tank, allowing fluid to come out of the cap end, and then we have a load or something. So this is a load that actually applies a force or something that pushes the fluid out, allowing the cylinder to retract. Alternatively, we could put a spring inside here. Typically it looks as a symbol for it, something similar like that. So that's a spring. There can be gas in there that gets compressed, and that compressed gas expands and allows for the cylinder to retract. There could be like a flywheel out here that this is connected to. So for example, this could be connected to a flywheel, and as this flywheel goes around, that angular momentum will actually push the cylinder back in. So there's lots of ways a single acting cylinder can act. The most common is going to be a single rod double acting cylinder, of course, as shown at the top there. So up until this point, we've actually talked about pressure as though pressure creates some sort of force. But in reality, that's not the way it works. Usually, if we have an end with some actuator here, okay, if this actuator actually has no load on it, okay, So let's say this has no load. Then so the resistance for it extending is none. Okay. Then technically there is no force or no pressure inside of this fluid, and therefore no pressure on the system. So basically what that means is that the pressure, the system pressure, is created by some load inside of the system. So that could be a mechanical load creating a hydraulic pressure. So a mechanical load here. And that mechanical load creates a pressure inside the system because of whatever that load is. It could be a hydraulic load. So we've used needle valves. Needle valves create a resistance to flow. And so that creates a hydraulic load. You could have line losses that are hydraulic loads. We could have a change in elevation, which is a hydraulic load. We're pushing fluid from one elevation to another. We can have a torque on a hydraulic motor that creates a load. It's a mechanical load converted to a hydraulic load. There's lots of ways we can create pressure, but the pressure is being created by some load, or whether it be mechanical or hydraulic. But there's got to be a load. If there's no load, then there is no pressure, and so especially once we ignore friction like line losses. Now, typically, in almost every instance, you're going to have line losses that's going to create some pressure drop. So in reality, you've always got some hydraulic load. Even though it might be minuscule, there is always some hydraulic load when you have moving fluid. But again, you're not going to have any significant load unless you have something like mechanical load on a cylinder or a torque on a motor or something of that nature. So there's a couple of things we need to consider, and I wrote this slide as problems with double-acting single-rod cylinders, but really it's not necessarily a problem. It's just something we need to consider. If we look at the area of a cylinder, if we look at what available area there is in a cylinder, let me see if I can draw a cylinder here with a piston and a rod. So on the cap end port, we have the full area of the piston here, right? So the full area. But on the rod end port, we only have the area that is not taken up by the rod, which is kind of interesting. So really, we have less area on the rod end than we do on the cap end. If we look at what that looks like, the cap end is just a circle. If we look at the piston from the cap end, we have this entire area available to us. But on the rod end, we have that same circle, same diameter circle, but we have the rod that takes up some area. So the area that pressure gets distributed over is somewhat less because the rod takes up an area of sorts somewhere. Remember, pressure is exerted in all directions, so it actually is exerted on the sides of the rod, the body of the cylinder. Okay, so there's pressure in all directions, but the only pressure that's creating force is the pressure that's on that piston. That's what's moving the rod. And so what we're really worried about is those arrows that's pointing along the area of the cylinder. So it'd be this area and this area. So this is the area for the cap end. Usually I do ACE and an area for the rod and ARE. So what is the area of the rod end? Well, the area of the rod end is just equal to the area of the cylinder minus the area of the rod. Okay? So we need to know the diameter of the cylinder and diameter of the rod. So what's the problem with this? Well, if you have a difference of areas, let me go to the next slide here. If we have a pressure So, for example, coming into the cap-in port of 1,000 psi, and then we have an area difference here inside of our cylinder. So there's going to be a greater area on our cap-in than there is on our rod end. Then we can have higher pressure coming out of our rod end port if this port is blocked. So, for example, if we show this port as being blocked, so if it's coming out here and it's deadheaded, okay, and we're measuring the pressure on this rod head port, we can actually have higher pressure here. You're like, okay, well that doesn't really matter, right? We've got a pressure relief gauge, or pressure relief valve. Well, if we've got a pressure relief valve that's, let's say, right here. Okay, let me draw me a little pressure relief valve in here. Then that pressure relief valve will only work up to, let's say it's set to 1,000 psi. Okay, then we can actually have 1,800 psi over here. And you're like, well, how is that? Well, it's the difference of area in that cylinder, and we're going to do some calculation with that. But what does that matter for us? Well, what if this hose over here what if it's only rated for 1,000? Now what happens? Well, you have issues with your hoses, right? So we've got to consider this difference of area. So we need to make sure that we are looking at that. So I want to look at the symbols for a cylinder. Of course, we've got this is a double-ended cylinder. This is we've got on the left-hand side here, we've got a single-acting cylinder, spring return. Then we have on the right of that, we have single-acting cylinder, spring extended. And then above that, we have a single-acting cylinder, external force return. And then, of course, here we've got our double-acting cylinder, single rod. Okay, we've got a quick little video here. I'm not going to play it. You can watch the video later, but because I don't want to, I'm going to upload this to YouTube, and I can't play somebody else's video on my YouTube video. But there's a video on this. If you watch the PowerPoint, you can get to see that. So let's look at the example one. We have a system that's set up so that at idle there's a 30 psi of pressure applied to both the rod end port and the cap end port of a double-action single rod cylinder. The diameter of the cylinder is 2 inches, and the rod diameter is 0.75 inches. The cylinder is mid-stroke but not moving due to a load on the rod. Calculate the net force on the rod. Okay, so what would you expect to happen if there was no load on the rod? Well, let's look at it first of all. So what this is saying, we've got some cylinder here, and it has some load on it. Okay, we've got on both ends of our cylinder, we've got, let's go ahead and connect them together here, 30 psi of pressure. Okay, so if we've got 30 psi on both sides, and what's the net force? Well, we can calculate that. So let's look at the area. We're going to use the area to find the force on both sides. So let's look at the area for the rod, or the cap end first. Area of the cap end. This is going to be equal to the 3 inches. So 2 inches. the area of the rod. We're going to say this is the area of the cylinder for right now. So the area of the rod is 0.75 inches divided by 2 squared times pi. So 0.75 divided by 2 squared times pi. That's going to give us 0.44 inches squared. So the area of the cap end is just the area of the cylinder, but the area of the rod end is equal to the area of the cap end, or the area of the cylinder minus the area of the rod. So that's going to be equal to 3.14159 minus 0.44. So we're going to get 2.7 inches squared. So what is the force on both sides? So we're looking at what is the force in this direction and what's the force in this direction. And we'll call this force of the cap end and the force of the rod end. So the force of the cap end equals our 30 pounds force per inches squared times the area of the cap end, which is 3.14 inches squared, and that's going to equal 94.24. So there's 94 pounds of force in the cap end. So the force of the rod end is going to be equal to our same 30 pounds force per inches squared times the different area. It's going to be 2.7 inches squared. So that's going to give us 81 exactly pounds force. So this is pounds force as well. So we have 81 pound force. Well, we know from Newton's law that if we have two forces opposing each other and one is larger than the other, then we have a net force in one direction. And if you have a net force in one direction, then we're going to have some sort of acceleration, right? So 94 pounds of force and 81 pounds of force. So if we do 94 minus 81, then we have 13 pounds of force in some direction. So I'm going to say that there is a 13 pound force on the rod. If there wasn't 13 pounds of force, then the rod would extend. So that's what this right here is asking. If there's no force on the rod, then what would it do? It would extend. You have to have 13 pounds of force. And that 13 pounds of force could be just friction, right? That load on extending could just be friction on the cylinder. The cylinder piston has seals to prevent flow from going from one side to the other. Those seals create friction. On the rod, we have a wiper and we have seals. That creates friction as well. So that friction can cause a load as well. So that 13 pounds of force could just be the force due to friction. Alright, so we have a double action single rod cylinder with a diameter of 1 inch and a rod diameter of 0.375 inches. If the rod import is blocked, preventing piston movement, and 400 psi is applied to the cap end, what is the pressure at the rod import? Well, first of all, let's find the areas. I'm not going to go ahead and go through all of this, but the area of the cap end is just going to be the 1/2 squared times pi, which is equal to 0.785 inches squared. And then the area of the rod is going to be equal to that 0.375 divided by 2 squared times pi, which is equal to 0.110. And then the area of the rod end is going to be that 0.785 minus 0.110, which is equal to 6.675 inches squared. So these two right here are the ones we care about, the area of the cap end, area of the rod end. We're not really too concerned about the area of the rod right now. So if we look at this, what we have is fluid being introduced, but it has nowhere to go. So fluid being introduced to the cap end at, it says right here, 400 psi. So we have 400 psi. That's going to create some force, but the rod can't move because the rod end is blocked, not allowing any fluid to escape. So the volume of the rod end can't decrease, allowing the rod to move. So that means that there has to be some force opposing the motion. The rod will be standing still, it won't be moving. So these two forces, if the rod's not moving, has to be equal to each other. And that force that's causing the rod not to move is because of the fluid. So this fluid has some pressure, but it won't be 400 psi because there's two different areas. So let's do this. We can figure out what the force is on the cap end. So force of the cap end is going to be equal to the 400 pounds force per inches squared times our 0.785 inches squared. And that's going to equal 314 pounds force. So we have 314 pounds of force, which means we have to have 314 pounds of force on the other side as well. So the pressure on the rod end equals that 314 pounds of force divided by the area of the rod end, which is 0.675 inches squared. And we're going to get a pressure of 465.18 pounds force per inches squared. There we go. So as we can see, the pressure was intensified by the cylinder. That's all we have for today. If you have any questions, let me know.